So we're going to start our next lecture. So this is the lecture for Wednesday, uh, April the 1st. We're going to continue working in the chapter 16 materials. So I'm going to head over to that page. So looking at see if I can get this a little wider so we can see it better. Yeah, we'll make that work. So looking at the material, the first thing I told you that we would start off with, the last thing we talked about on Monday was polyprotic acids, and we talked about monoprotics versus diprotics and triprotics. We saw a few examples of those in our end of chapter problems that we worked yesterday. So the first thing we're going to look at going forwards is looking at the quiz questions that you had for the material we cover on Monday. So again, I told you you're going to have these for every lecture. So tomorrow they'll open up another one, and it will be due on Thursday evening. So you'll have Wednesday and Thursday to work on that material. So the first question says, which one of the following is not a conjugate acid-base pair? So if we look at these two things, to be a conjugate acid-base pair, it means they need to be separated by a proton. And with this example of ammonia, NH3, going to ammonium, NH4, it's accomplishing that by adding a proton to it. So it also could be part of a conjugate acid-base pair if it lost a proton. And if it lost a proton, it would be going to form the amide, so NH2 with a minus. So it could work either way in the system. So when we look to answer this question, we're looking for the one that is separated, that is not separated by a proton. So it says for the one that's not. So if I look at sulfate and bisulfate, the only difference is the extra proton. So if I started with this material and wanted to get to this one, all I have to do is lose off a proton. So this is a pair, so it is not that choice. If I look at the next one, so sulfurous acid and the bisulfite ion that go with that. So to go from one to the other, all I would have to do is to lose off a proton in the system. If I look at the one below, this was formic acid, and formic acid would have to lose off one proton, and it would become the formate ion. So the last one was actually the correct answer in the system. So I'm going to fill that one in. The problem with this one is that if we had the OH minus hydroxide, if we add a proton to it, so it's working as a base, that gets us to water, H2O, but it doesn't take us all the way to the hydronium ion, H3O. So to get to there, you would have to add a second proton to it. So what that means is these are separated by more than the gain or loss of a proton. So this would be the one that would be my correct answer for this first clicker question. And those of you that did it did very well on that. The second question asks, which one of the following acids has the largest value for Ka? So if I'm looking at Ka, Ka is describing the strength of the ionization constant. And the larger the value for Ka, that means that the stronger the acid is in a system. So the larger the value of Ka, the more the equilibrium for the dissociation lies in the forward direction. So I would expect to see more of the proton and the conjugate to that weak acid in the system, the larger the value for Ka. So a larger Ka yields more of these guys as products. Now on this particular clicker question we had, we're looking at how many protons are present in each one of the systems. So if I look at acid 1, there are 2 protons present in the system. and acid 1, there's only 1. But if I look at acid 3 has 3 protons. So that means the equilibrium is furthest to the right with acid 3. And if it's the one that's furthest to right, that means that it's paired with the one that has the largest value for the Ka. So on this, I'd expect the correct answer to be answer 3. All right, so those are going to be the type of clicker questions that you can expect to see. Again, you have to complete those by midnight. So the next 2 days. So you have to do them by Tuesday night at midnight, which is actually it's Wednesday at 12 a.m. or 11:59 p.m. if you want to think of it, to keep it in the same day. But I'm giving you the 2 days to do the quiz, and it'll be the same for the next one on the notes that we're posting today. Okay, so the next topic we will look at is the concept of what it means to undergo autoionization. So if we look at the concept for the autoionization of water, water is an amphoteric substance. So that means it can either act as an acid or a base, depending on what it's reacting with. And we've seen that in several examples so far in this chapter. But there must be some ions present in the system. So what happens sometimes is that water will react with itself, and that one molecule serves as the acid, the other would serve as the base when it forms the ions. And whenever it reacts with itself, the name for this process is called autoionization. And there's another name we give for it as well. We also call the other name self-ionization. So autoionization has the same meaning as self-ionization in a system. But if we look at the reaction that's given below, what's happening in autoionization is that two molecules of water would react with one another, and the proton is transferred from one molecule of water to the other. So in this case, if they're drawn out in order, the proton's transferred from the molecule on the right, it's left with the OH minus, and on the left it picks up the proton and becomes a hydronium ion. So essentially, when we're writing this one out, we're saying this is equivalent to two water molecules working together. So this would be two H2O liquids working together in the system, as opposed to two individual singles. But we also can look at it as a single water molecule. Instead of writing as the hydronium H3O plus, we can just write it as the H plus, and it still represents the same thing, because we've talked about that H plus and H3O plus in an aqueous solution have the same meaning to us. So as long as there's water around, those are equivalent to one another. So we can get rid of the second water molecule. If it's there, it's just being added to this H plus to form the hydronium. So a lot of times we write it without. So when we look at solutions that contain both the H3O plus, the hydronium ion, and the hydroxide, the OH minus, and if the concentrations of these ions are equal to one another, like they are in pure water, that is a unique case in aqueous systems. So this only happens at one point where those concentrations are equal, and it's true when the concentrations are equal to 1 times 10 to the minus 7th molar at 25 degrees. So now if we think about writing an expression to describe this, so the expression that describes this would be the product of the hydronium times the hydroxide, and it should give the same number. Well, the y of it is that if we go back and think of this ionization that we would have, so I'm going to write it for the one down here in the bottom. So if we look for this guy, and if we write its equilibrium constant, so I'll try to do that in blue, or the equilibrium constant expression, we give it the name Kw, and it would be products over reactants. So the products are the H plus, the reactants are the OH minus, and then, sorry, the products are the H plus and the OH minus, the reactants are the water molecule. But since the water molecule is in the liquid state, it doesn't appear in the K expression. So the Kw is simply the product of the H plus times the OH minus in the system. So we call this product the ion product of water. Back to my highlighter. And the ion product of water has the symbol of Kw. And it's also called the dissociation constant of water. And it's simply equal to the concentration of the hydrogen ion or the hydronium times the hydroxide, and it's equal to a value of 1 times 10 to the minus 14th at 25 degrees. Now, the thing this allows us to do is knowing this relationship. If I know one concentration, either the H plus or the OH minus, I can always go determine what the other one is. So if I know, if I can measure or determine what one is, I can use that piece of information, this formula, to determine what the other compound is, or the other quantity. We can calculate the other one. Also, when I look at the two things, and I know since they're directly related to one another in an equation, that is, if one increases, like the hydronium ion increases, in order for them to still be equal to this constant Kw, the other one has to go down. So in this equation where they're multiplied by one another, they are said to be inversely proportional. So one goes up, the other one goes down. So if the H plus were to increase, the OH minus has to respond by going down. And the converse is true. If we looked at the OH minus was increasing, the system would have to respond by the H plus would decrease or go down in the system. So when we look at solutions and we determine the nature of the acidity in those, one way that that we quantify that is by looking at the relative amounts of the H plus and the OH minus. And we define solutions in a generic way, define them either neutral, acidic, or basic by doing a comparison of the hydronium and the hydroxide ions. So neutral solutions have equal amounts of H3O plus and the OH minus. And that only occurs at one point. So this, imagine the negative's not here. Let's see if I can block that the negative out somehow. So let's, that's not gonna do it. And it won't let me get a white pen. I don't have a full tool book on this. Let's try that shapes thing again. All right, so if I draw my shape around that, and probably more trouble than it's worth here. I think it is. So, all right, so let me do it this way. Let me delete that. Okay, that's not a negative. So I don't want to make sure you understand that's not a negative in the system. So neutral solutions have equal concentrations of H plus and OH minus. And with those two things being multiplied to against one another, that only happens when they're at 1 times 10 to the minus 7th molar. Okay, those concentrations have to be 1 times 10 to the minus 7th molar. By definition, an acidic solution has a larger concentration of the hydronium ion than the hydroxide. So if that's true, the hydronium ion is something greater than 1 times 10 to the minus 7th, and the hydroxide is something less than 1 times 10 to the minus 7th. And the third possibility is the basic solution. For a basic solution, it has a larger OH minus concentration than it has the H3O plus, the hydronium. So that means that the H3O plus is less than 1 times 10 to the minus 7th. And now the OH minus is something greater than 1 times 10 to the minus 7th. So here's an example of a problem that we might run into in doing these types of analysis. So the problem asks, there's where I was trying to change my line properties. The problem asks is calculate the OH minus at 25 degrees when the H3O plus is 1.5 times 10 to the minus 9. So the way that I want to approach this problem is recognize the relationship, so that H plus is equal to OH minus, or is equal, H plus times OH minus is equal to KW. So what I'm looking for is what is the OH minus. So if I rearrange this, it says that the OH minus is equal to the KW divided by H plus. So KW has a value of 1 times 10 to the minus 4th, or 14th. And we just said that H plus is 1.5 times 10 to the minus 9th. So if I divide those out, really looking for my calculator, which I can't determine or find. So I've got to use y'all's favorite calculator, but the one I don't know how to use at all. So I'm stuck with this TI 83 plus from hell. Let's see if I can figure something out on it. Divided by 1.5 e to the minus 9 parentheses. All right, and when I divide that out, I think I get a right number. I get 6.67 times 10 to the minus 6th molar. All right, so it's 6.67 times 10 to the minus 6th molar. And if I need to try to figure out which one of those is that, is it acidic, basic, or neutral? And I really could answer that question by looking at what this first term is. So the fact that the hydronium ion is less than 1 times 10 to the minus 7th, that tells me that this is a basic solution. All right, so we said a basic solution was something where the hydronium ion is less than 1 times 10 to the minus 7th. And the hydroxide, what we've got here, is something greater than 1 times 10 to the minus 7th. And this is a case where it's greater than 1 times 10 to the minus 7th. So we need to be able to look at a solution and determine is it acidic, neutral, or basic. So one of the common ways that we quantify the acidity, or the amount of acid concentration that exists in the solution, is with this term called pH. It's a measure of acidity, and it's also a measure of basicity. So either of these terms can be expressed by pH. Now, pH is equal to the negative log base 10 of the hydrogen ion, or the hydronium. So if we look at what is the pH of water itself, pure water has a hydrogen ion concentration, we said, of 1 times 10 to the minus 7th. So if we take the log of that, the negative log of 1 times 10 to the minus 7th is 7. And if we wanted to have some zeros and accuracy in here, which maybe makes it look a little better. So if this number was 1 times 10 to the minus 7th, that means that when I took the negative log of that, it would be 7.00. So if I want to know what is the pH in the system, if that's the unknown, to be able to calculate that, I have to know what is the hydronium ion concentration. Now, if we go back and compare to our acidic and basic nature, and those definitions that we just put forward, what happens is that if something has a pH of less than 7, it's defined as acidic. If something has a pH of greater than 7, it's basic. And if pH is equal to 7, it is neutral by pH. Now, we just looked at the formula for to calculate pH. So we said that pH is equal to the negative log base 10 of the OH minus, or the hydronium ion. So either the H plus or, in this case, we're using the H3O plus, the hydronium ion. It's the negative log of either of those. Now, if we want to go from the opposite direction, if we know pH in the system, so this is a known, and we want to know what the H plus is, we need to be able to undo this P function that we took. So we take the antilog of both sides, and if it's a log base 10, it's 10 to the negative pH. And 10 to the negative pH would be equal to the H3O plus. So that's an equation we need to be able to utilize, and we'll do some examples of that in the upcoming material here in the next few slides. And if we go back and remember our equation, the equation that we had that put a relationship between the two things says that the H plus times the OH minus is equal to KW. And again, I wish the authors would have thrown some decimal places in here, but they didn't. They just left it pretty generic. Okay, so now if we think about these P functions and applying it to the term of pH, here are some examples of things that are common substances that we encounter and what the pHs would be. So we'll start with things that are near the middle, so near neutral pH. And there's not a lot of things that are near neutral pH. Most things are a little bit higher or lower. If we look at example rainwater, and you may be thinking, well, why would rainwater, if it's unpolluted rainwater, why would not be pH 7 the same as pure water from the lab? And the reason for that is rainwater is saturated with carbonic acid. So H2CO3 is carbonic acid. And we know that that's present in the atmosphere today between 400 and 500 parts per million. So there is a significant amount of this that's dissolved in water. And when it dissolves in water, being a weak acid, it can lose its proton off to form the proton plus the bicarbonate ion. See if I can get that in there. And this presence of the proton causes the pH to drop because there's excess proton there. So even pure rainwater is not pH 7. It's significantly below that. So if we go to the, just work up the list just a little bit, most of the beers that we drink are between pH 4 and 5. Some of the fruits are a little bit more acidic. So apples, peaches, and cherries range from pH 2.9 to on the upper end are almost 4, but they're all acidic. Most of the wines that you would drink are in the neighborhood of pH 3. Some fruits are pretty acidic. A plum is down typically a little bit below 3. Soft drinks, if we look at something like one of the ones that's the strongest in terms of the acidity is typically a Dr. Pepper. Dr. Pepper has a little bit more phosphoric acid in it than some of the other soft drinks, and it takes its pH down to near 2. In fact, Dr. Pepper is so acidic that we have a stringent guideline of things that we can neutralize in our lab versus consider it as waste versus it's neutral enough we can pour it down the sink. And our pH range is plus or minus 3 of neutral, which is pH 7. So anything beyond more acidic than pH 4 or more basic than pH 10, I can't put that down the sink if it's something we made. So by following the rules that are given to us by the city of Durant, we can't put a synthetic soft drink that we made, pour it down the sink because it's too acidic. We'd have to neutralize that some before we could do that. If we look at other things like lemons are even more acidic, down in the low twos. Limes are slightly more acidic than that. And when you get to the things in the stomach, it varies from pH 1 to as high as pH 3. It depends on if there's a bunch of food there, the stomach releases the hydrochloric acid, which drops the pH down closer to 1. If your stomach's for the most part empty, it's a little higher. It's up around pH 3. Now, if we look at things that are basic, which are represented in the blue color, one of the important ones we need to understand is what's called physiological pH. And what is the pH of human blood? And typically we say that number is close to 7.4. And that is actually a very good indicator of the health of a human being. So when you go to the doctor and they run this Chem 20 test, that's one of the first things that they look at, because it's a simple thing to measure what is the pH of your blood. And then if it's within 0.2 units high or low, there's something extremely low with your human health. And it can be either way. It can be high or it can be low. If we look at something like egg whites are closer to pH 8. Milk of magnesia is an antacid material that's closer to pH 10.5. Ammonia that you might use for cleaning with is somewhere in the neighborhood of 11. And a 4% solution of sodium hydroxide, which is a strong base, is a pH of 14. That's about a 1 molar solution. And that's what we would call a caustic solution. Now, when we start taking logs of materials, we have to be aware of how to do the calculations for logs. And if we're doing log base 10, we can break that up and look at the type of the parts to the calculation that we do. So let's say I had the number 2.0 times 10 to the minus 6. Now I could use the dissociative property of a log, and the dissociative property of a log says that log of A times B is equal to the log of A plus the log of B. So if I wanted to look at this number, I could break it into two different terms. I could break it into this term, log of 10 to the 6 plus log of 2.0. All right, so now if I want to do the conversions, log base 10 of 10 to the 6 is simply 6. And then log base 10 of 2.0 is 3.303 repeating. It's this number. So when I add those together, I would see that it's 6.303. So something I want to show you, that if you looked at doing scientific notation and something that's in scientific notation, doing the log of it. So if I had the number of log of 2.0 times 10 to the 4th. So if I look it up and break that up into two different terms in the same way, this simply would become 10 to the 4, and log of 10 to the 4th is simply 4. So the answer of that would be equal to 4.30303, and it's a repeating as it goes along. So what that means is when we have a number raised to scientific notation, that when we take a log is represents the first number before the decimal. So if it's a huge number, it just tells us how big the exponent is in the scientific notation. But it really doesn't have anything to do with the accuracy or the precision of the calculation. That is in this component of the calculation. So when we take a log of something to know where the number of significant decimal places are, the number of significant decimal places is determined by the number of digits after the decimal point in the log. right? So if we would look at this number, 2 times 10 to the minus 6. So the significant digits are 2 significant figures here. And when we take the log of this, it would be 6.30, and we need to round this to the number of significant figures we have. So we would terminate these terms off. It would just be 6.30. And these are the 2 significant figures that we have in that number. This 6 up in the front just represents a spacing digit. So if I undo a log, so if I wanted to undo this function, and let me just show you this right quick because I didn't make a slide on this. So if I wanted to undo that, what I would do is to take the anti-log, so 10 to the 6.30, and that would equal to 2.0 times 10 to the minus 6. There are 2 places past the decimal in the number that I want to take the anti-log up, and that corresponds to 2 places or 2 significant figures in the number when we've done the calculation. Okay, so that's kind of a quick overview of logs. So let's continue to talk about our topics. So what does that pH number imply? The lower the pH, the more acidic the solution is, and the higher the pH, the more basic the solution is. And what the pH scale means is that 1 unit on the pH scale corresponds to a difference in factor of 10 of the acidity or the concentration of the proton. Now, the normal range that we describe the pH scale is 0 to 14. But I want you to understand that that's not the end to it. So it is very possible to have values that are at a -1 for the pH, or that are at a value of 15 for the pH. So those are not things that are not possible. So when we look at something that's pH 0, so pH 0 would imply that the hydrogen ion concentration is at 1 molar. Okay, so pH 0 would mean that the hydrogen ion concentration is 1 molar. And on the other end of the scale is that if pH is 14, it would imply that the OH minus is 1 molar. So if we go down and look at the basicity scale and plot it as POH instead of pH, that would be at 14 would correspond to 1 molar of the OH minus. So again, as I just mentioned, the scale can be negative and it can be larger than 14 for very, very alkaline or basic solutions. Okay, so if I look at these numbers and compare the pH scale and the pHO scale right next to each other, what I'll see that any point, if I were to take and add both pH and POH together, I would see that the 2 things would add together to be 14. And it doesn't matter at which point that you're at in the scale, the 2 things would always add together to be 14 in the system. So plus needs to go up there. So they add together to be 14. So the relationship is that pH plus POH for water or an aqueous solution always adds together to be 14. And that's a valuable tool that we'll use for things. So I've mentioned this POH. Let me go through and explain exactly what it is in a little bit more detail. POH is simply the negative log of the OH minus. So if I want to know what is the OH minus and I have the POH, I just take 10 to the minus POH, or the negative anti-log. So if I look at what is the POH of water, pure water, it is the negative OH minus, negative log of the OH minus, and it's 1 times 10 to the minus 7th, so it would be 7. And usually we write it with another 0 or 2 in there. So if I need to know what's the OH minus, or I need to know what is the OH minus if I want to know what is the POH. And going back to our definitions, if POH is less than 7, it's basic. If POH is greater than 7, the solution is acidic. And if POH is equal to 7 exactly, then it is a neutral solution. And the combination, as I showed you from adding together the terms from these previous slides, when we compare pH and POH together, pH plus POH equal to 14. Now, why has that happened? We'll get to that in just another slide or two. But let's do a calculation with POH. So on this one, it says calculate the pH when the OH minus is 1 times 10 to the minus 2. So there's a couple of different ways that you could work this problem. And I think I'll just split the page and show you the two approaches that you could use. So one way would be knowing that H plus H plus times the OH minus is equal to the KW, which is equal to 1 times 10 to the minus 14th. So from that, I could find out that the H plus is equal to KW divided by the OH minus. And the KW is 1 times 10 to the minus 14th. And the OH minus, we said in this problem, was 1.32 times 10 to the minus 2. So we'll just find out what that equals to. Again, a calculator I don't know how to use hardly at all. And then find that the H plus is 7.7 times 10 to the minus 13th. All right, so if I know that, I can calculate what pH is then. So pH is equal to the negative log of the H plus. So it would be the negative log of 7.7 times 10 to the minus 13th. And let's see if I can figure out how to do that. And I know there's a way to put answer in here for your previous answer. I just don't know how to do that. So I'm going to write out 7.7 e to the minus 13th. And it tells me that it didn't like that at all. All right, so once I learn how to use the calculator a little bit, it gives me a value of 12.1 or 12.11. So 12.11, that's substantially greater than 7. So if it's greater than 7, that means it's a basic pH. So that would be one way to answer that problem. But let me show you a different approach that'll get you to the same place. So if I know that what the OH minus is, I can simply find out what is the POH. POH is equal to the negative log of the OH minus. So it's the negative log of 1.32 times 10 to the minus 2. And same in the calculator, I have the same issue. So the negative log, oops, clear, negative log of 1.32 times 10 to the minus 2, and I find that that is 1.9. So if it is 1.9, and if pOH is less than 7, that implies that the solution is basic as well. The other way that we could quickly go to pH, we said that pH plus pOH was equal to 14 in all cases. So if I know what pOH is and I want to know what pH is, I simply do a subtraction. So pH is equal to 14 minus pOH. And when I subtract that out, I find that it's 12.1. So I get the same answer either way, and both things tell me that the solution is basic in nature. Okay, so this table is a table that I borrowed from a different textbook, but it looks at the comparison of how the hydrogen ion changes with pH, and then in the middle it's got a graph representing to try to visualize what represents a large amount of the hydrogen ion concentration to very little, and that the two things for pH and pOH are oppositely paired from one another. So starting at pH 0, that means that the hydrogen ion concentration is 10 to the 0 power, or it's 1. So that's a bunch of proton around. So if it is 0, since I said that pH plus pOH have to equal 14, that means that pOH is 14 and the hydroxide ion is 1 times 10 to the minus 14. So there's just a tiny amount of the OH minus around. So if I jump up to like pH 5, pH 5 means that the hydrogen ion is at 1 times 10 to the minus 5th. So there's a moderate amount, there's some around, but the OH minus concentration is going to be equal to 1 times 10 to the minus 9th because pOH is 9. And if I go further to 7, if pH is 7, pOH is 7, and both the concentration of H plus and pOH or OH minus are both 1 times 10 to the minus 7th. And if I go to the other side of the scale, so 10 to the minus 13th, at 10 to the minus 13th corresponds to pH 13, is only a trace amount of hydrogen left, but now the OH minus is huge. So the OH minus is here at 0.1 molar, or pOH of 1. So the thing that we see when we start to realize what this graph is saying is that the things are tied together, and every jump of 1 in the pH scale is a power of 10 on the hydrogen ion concentration scale. So if I wanted to do a comparison between something at pH 3 and pH 7, that tells me that it's 4 orders of magnitude higher concentration, or 10 to the minus 3rd versus 10 to the minus 7th, which is 4 orders of magnitude of difference. And it's getting smaller and smaller and smaller. Each time I go up a unit on the P function scale, it's getting a factor of 10 less concentrated. Now, on the opposite side, we take, and these things would be small to start with, and every time I go up by a factor or 1 on the P function scale, it's getting a factor of 10 larger. If I go, in this case, I do a step of 2, it gets 2 orders of magnitude larger. And if I went from 9 to 3, okay, that is a step of 6 units. And I would expect it to go from 6 orders of magnitude. So 10 to the minus 9th, 10 to the minus 3rd, so 10 to the minus 6th. Just start to learn what the pH and pOH scale mean in terms of which one is the largest, and then secondly, what it means to change from one pH to another pH in terms of the relative concentrations. And it really, once you start to learn the way that logs work in calculations, it's not that hard to figure out. All right, if we look at the relationship we have between pH and pOH adding up to 14, and we saw those on all of the cases on this page, so I'll just point a couple out to you. So here at 11, so pH was 11, pOH is 3, I add together and I get 14. And if I go to here, it's 9 and it's 5, and they add together to be 14. And I go to this extreme, it's 1 and it's 13, and they add together to be 14. So pH plus pOH always equals 14. Well, what's the why of that? Why is that whole possible? So where that comes from is this equation is a derivation of the ion product constant of water. And the ion product constant of water said that that Kw was equal to the hydronium ion times the hydroxide ion concentration. And we know that Kw at 25 degrees is 1 times 10 to the minus 14. So what we're going to do is take the negative log of both sides. So the negative log of everything on the left-hand side and the negative log of everything on the right-hand side. Now we're going to use the dispersive property of a log to separate this into two terms. So the first term becomes the negative log of H3O plus, and then plus the second term, the negative log of the OH minus. And then we've got the negative log of 1 times 10 to the minus 14th on the right, but that's just a numerical value. That's equal to 14 when I plug that into a calculator. Now, by definition, the negative log of the OH minus of the H3O plus is pH. The negative log of the OH minus is pOH. So this becomes our equation, pH plus pOH equals 14 in the system. All right, another way that we express something about the strength of acids and bases is with the pKa values. So we talked a little bit earlier in the chapter about the acid-base ionization constants for weak acids. And we looked at the numbers being very large at like 10 to the minus 2 for something that was a very strong weak acid, and we went all the way down to phenol with something that had a Ka of 10 to the minus 10th for something that's a very weak acid. A way that we express those is we take that same P function now of the Ka or the Kb. So the pKa is the negative log base 10 of the Ka. The pKb is equal to the negative log base 10 of the Kb. And if we want to undo that, if we know what the pKa is and want to know what Ka or Kb is, it's the negative antilog of the pKa or the negative antilog of the pKb. Now, a lot of the stuff that we'd been doing in the previous chapters, our logs were based Ln. And what we're doing in this chapter, we got to be clear that we understand these are log base 10, not log base E. So log versus Ln log, natural log. So the stuff that we did with the Arrhenius equation, it was a natural log. These are not natural log. These are log base 10s. So when we take an antilog, it is 10 to the power of x is our antilog. So when we want to get rid of something that we've taken a p function of or undo that p function, it's 10 to the minus whatever the p function is for that term. So Ka is 10 to the minus pKa. Kb is 10 to the minus pKb. Now, some things that we learn or information that we see is that the larger the value of Ka means the smaller the value for the pKa. And the stronger the acid is going to be, the smaller the value of pKa is going to be, because we said the larger the Ka, the more the equilibrium lies in the forward direction. So more it goes in the forward direction, the more the proton comes off. And the reason that it's a smaller for the pKa is that it's a negative function. So this it's a negative log that we're taking when we take the P function. And for a base, it's just the reverse. The stronger the base, the smaller the pKb is in the system. So the larger the Ka, the smaller the pKb is going to be in a problem. And some of those we're just going to have to learn by doing examples with them. All right. Now, when we think about solutions that are mixtures of water, and they may have a strong acid just dissolved in water. So if it's an aqueous solution dissolved, has a strong acid dissolved in it, the two sources of the hydronium ion can be from the water molecule itself or from the acid. But what happens, we know the ionization that comes from the water molecule itself is weak. It's only 1 times 10 to the minus 7th. So what that means is the contribution from the water to the total concentration of the hydronium ion concentration is really insignificant, so much that we can neglect it in the calculations. What happens is the hydronium ion shifts the Kw equilibrium so far that the ionization of the water is too small to be significant. So when we want to know what is the hydrogen ion concentration for a strong acid system, it's simply equal to the concentration of that strong acid. And sometimes I write these a little bit different than the textbook. I will write it as a lowercase c to represent the concentration of the strong acid, and that it's just equal to whatever that concentration is equal to the molar concentration of the hydronium ion. For say, or example, if I had 0.1 molar hydrochloric acid, a strong acid, that would tell me that the concentration of the H plus is equal to 0.1 molar. All right. So here's some examples of some problems and things that might be old test type questions, and I think most of these are. So the first one says the pH of rainwater collected in a certain region of the Northeast United States was 4.82 on a given day. What is the H plus ion concentration of the rainwater? So I want to know what was the hydrogen ion concentration, or I'm wanting to know what is this term in the system. So we know what pH was, and we said that H plus is equal 10 to the minus pH. So I would just take that information and take the negative antilog of the pH, so 10 to the minus 4.82. So this is where you and your calculator need to get along a little bit. And this is where me and my TI 30 or TI 83 plus may not get along. So I got to put the negative in first. 2. And let's see, do I have to put the, yep, I got to put the 10 to the x in first. So let me clear this. So 10 to the x and then negative 4.82, close parentheses. And I find that the hydrogen ion concentration is 1.5. I've got 2 significant figures in this. So that means on this, I need to have only 2 significant figures, 1.5 times 10 to the minus 5th molar of the hydrogen ion concentration, H plus. Okay, so the next question below asks what is or says the OH minus ion concentration in a blood sample is 2.5 times 10 to the minus 7th. What is the pH of the blood? So the approach that I would use is to find what is POH. So POH is equal to the negative log of the OH minus. And I know what that is, so it's equal to the negative log of the 2.5 times 10 to the minus 7th. So I'm going to find out what that number is. This is going to force me to learn the calculator I hate most in life, but y'all get to laugh about it. And I get that that number is 6 point. I've got two significant figures in this component in the calculation, so I need to go 2 places past the decimal, 6.60. And then if I want to know what pH is equal to 14 minus POH. Just simply rearranging that formula. So 14 minus 6.6. And I find that the pH of that solution is 7.40. All right, so in terms of human health, 7.40 is exactly physiological pH. So that tells me that that's a healthy individual in the world. All right, so what happens if we have a weak acid in the system? And how do we have to deal with it? So if we have the weak acid in water, the sources for the hydronium ion become the self-ionization or the ionization of the weak acid and from the autopyrolysis of water. This is a little bit more complicated calculation in the fact that the weak acid undergoes a partial ionization. And if we want to solve this, it involves the ionization equilibrium. So the weak acid is represented by HA. So this is our weak acid plus water yields the conjugate base and the hydronium ion concentration. So the approach that we have to use to this, it depends on what this Ka value is for these weak acids, because the larger the value for the Ka, the more this equilibrium is going to lie in the forward direction. So that means that the equilibrium is going to lie further to the right in favor of the products. And it would produce more of the hydronium ion and would therefore have a lower pH in the system. So we've got a variety of different values of Kas, and we've talked about these already. So pKa's vary from close to 2 to close to 10, and we've got the Ka values in between these. Again, remember, if we want to go in between them, pKa is simply equal to the negative log of the Ka. So we have a conversion factor that lets us go in between those two things at any time. So if we want to find the pH of a weak acid, what we have to do is set up an ice system and use it as a guide to understand the ionization that's occurring. So we complete the ice table based on the information that's provided to us. We have to keep in mind what is the stoichiometry in the change line. So where we have minus X or plus X or minus 2X. And then we can substitute in for the equilibrium concentrations in the K expression. And we determine the hydronium ion from the calculated value of X and calculate that to pH as necessary, and then check your answer. Well, sometimes it's not really obvious to check how you would check your answer. Maybe you can make an educated guess to see that it's approaching the value that you need to have. Another way to measure the strength of an acid determine its what percentage of the acid molecules ionize when it dissolved in water, and that's called the percent ionization. So the higher the percent ionization, the stronger the acid has. And we call the concentration of the ionized acid. So if we look at a weak acid, dissociates to the ionized form of the acid plus the H plus. If this is the major contribution to pH and water's not playing a factor, You don't get one of these guys without forming one of these guys. So this is the ionized form of the acid, and this represents the hydronium ion, H3O plus. The two things would be equal to each other. You can't get one without the other. So when we determine the percent ionization, it's the concentration of the ionized form of the acid divided by the initial concentration, and multiplied by 100 is the percent. Or if we can determine the pH of that system, it's the hydrogen ion concentration divided by the initial concentration of the weak acid times 100%, because we say these two things are equivalent to each other in this statement above. And we'll look at examples of that as we go further in the chapter. Okay, so well, what's the catch? And the catch is that there's a relationship between the concentration of the acid and the hydronium ion concentration. If we increase the initial concentration of the acid, it results in more hydronium ion being released. So the lower the pH would be. But as we increase the ionization of the weak acid, it also causes a decrease in the percent of the ionization. So this means that the increase in the hydronium ion concentration is slower than the increase in the acid concentration. So it's not just a fixed relationship where I can say that for acetic acid, 10% of the protons are going to come off and it's 10% ionized all the time, or 5% or any other number. What happens is that extent of the ionization changes with the concentration of the acid. So the hydrogen ion concentration for a weak acid increases as I increase the concentration of the acid, but the percent ionization decreases as I increase the concentration of the acid. Those two things are fighting each other and going in opposite directions. Now, how do I deal with it when I have mixtures? If I have a mixture of a strong acid and a weak acid, what happens is the ionization of the strong acid is complete, and it provides enough protons that it suppresses the ionization of the weak acid to the left, so that the ionization of the weak acid is something that's negligible, we don't have to consider. Now, what the heck am I talking about? All right, so let me try to illustrate that. So I've got a strong acid, HX, and it dissociates 100% to H plus and the conjugate base X. And now I've got a weak acid in here, and I'm going to represent the weak acid with HA. Now, the weak acid is in equilibrium, so it's in equilibrium with H plus and the conjugate base A minus. But the fact that the equilibrium at the top is a full ionization, so this fact that this is 100% causes the hydrogen ion concentration to increase both top and bottom. And we know with Le Chartier's principle, as one of the product concentrations goes up, the system responds to relieve stress by going in the reverse direction. So essentially, the presence of a strong acid suppresses the ionization of a weak acid to the point where we don't even have to consider this equilibrium going in the forward direction at all. Now, if it is a mixture of two weak acids, life gets a little bit more complicated. Usually we just consider the stronger of the two, provided the values of Ka are separated by at least 2 orders of magnitude. And what happens is the one that is significantly stronger has a similar effect as the strong acid on the weaker ones. But if the Ks are not separated by 2 orders of magnitude, it's a much more complicated problem. All right, so when we look at strong bases, how do we approach those? So what happens with a strong base, let's get that back and get my highlighter. What happens with a strong base is that a strong base is willing to accept a proton to neutralize it. And this is water becomes what we call the standard acid. So ionic bases like sodium hydroxide, almost all of the units are dissociated in the hydroxide and the sodium. They're strong electrolytes. And even if they're multi-hydroxides, they will dissociate completely. So something like calcium hydroxide that has multiple hydroxide atoms on it, it would still completely fall apart to form the calcium 2 plus 2 hydroxide minus anions. So, and it's 100%. It's going completely to the right. There's no left arrow to it. Now, if it's a weak base, it's a partial. So if we look at what happens with a weak base, something like ammonia, ammonia undergoes through, say, a fraction of the molecules except the H plus because they're weak electrolytes. And they don't take a significant amount of the hydrogen ion from water. Most commonly, the percent of ionization of a weak acid of a weak base is less than 1%. So what happens is that the hydroxide ionized concentration is typically much, much less than the concentration of the weak base. So what we're assuming is that as this weak base goes forward and reacts with water, is that it doesn't go to the extent where it contributes a huge amount of hydroxide to it. So the way that we have to approach finding the pH for a weak base is similar to that of what we have to do with a weak acid. Now, we haven't talked about what that is yet, but we're fixing to get there in our slides. Right, so when we write out our KB expression, it's similar to the Ka expressions that we had been writing previously in the chapter. So our Kb is our base reacting with water to produce the hydroxide and the BH minus. And we call this the base ionization constant, or the Kb. And because the water is the liquid in the system, it doesn't appear in the expression. So products over reactants, the Kb is just the concentration of the conjugate acid times the concentration of the OH minus divided by the concentration of the weak base, and that's equal to the Kb. The water doesn't show up in it. And the larger the value for Kb, the stronger the base is in the system. All right, so here's a table of some of the common bases that we run into in problems. The carbonate ion, and the carbonate ion can pick up a proton from water and form bicarbonate and produce the OH minus. It has a Kb of 1.8 times 10 minus 4. Methylamine is one you'll learn more about in organic chemistry, but primary amine functions can pick up a proton to form the protonated ammonium form of it, and it produces an OH minus as well. Its Ka is about 10 to the minus 4. Ethylamine is very, very similar, and it's near 10 to the minus 4. Now, ammonia, NH3, is a little weaker. It can react with water to produce the ammonium, NH4 plus, and the OH minus. It's around 2 times 10 to the minus 5th. The bicarbonate ion, this was the product from the carbonic acid, so these are the same species. It can react with water to form carbonic acid and kick off an OH minus, but this one's an even weaker base. It's 2.3 times 10 to the minus 8. So if you remember our thing that we talked about with the comparison of the strengths, the larger the number, the stronger the base. So I'd have to, let's see if I can write on this sideways. So wow, this looks very weird to me. I don't know what it's going to look like on the screen. Stronger. So stronger base. That is very hard to do. And then a couple more on the bottom, and these are even going to things that are slightly weaker in terms of their strength. So pyridine is to the minus 9th. Alanine is to the minus 10th. and all of them have the common characteristic that they're kicking off the OH minus in the system. Okay, so what we want to do from there, and then this slide just gives an idea of what these things have in common. And we talked about this with the Bronsted-Lowry. So we said things that were bases had lone pairs of electrons, and those were the acceptor of the proton that was donated from the Bronsted-Lowry acid. So all of these things, ammonia, methylamine, pyridine, these structures have lone pairs of electrons that's going to accept that proton that doesn't have the electrons in it. So where we're going to pick up on Monday is talking about how we deal with the calculations, because the calculations for the weak acid, weak base system are a little bit more complex. So with that, I'm going to stop this video. We went about an hour and 12 minutes, so that's typically what a class time is going to run anyway. So watch the video, do the quiz, and we'll have more stuff due on Monday. We'll go back in the notes, and then we'll finish up the chapter and probably start. If we don't finish the chapter on Monday, we'll definitely finish the chapter on Wednesday in class, and then go right into chapter 17. Okay, so have a good weekend. Make sure you work on that lab as I get things posted for you. And if you have questions, post a discussion board question, send me an email, show up on into the Zoom office hours, just however you want to approach doing it. So over and out.